Welcome to Get Your FRQ On. This question is from 2010. It's question 6, and it is not calculator active. In the question stem, we are provided with two differential equations, one for dy dx and the other for d squared y dx squared. And we are provided with an initial condition that f of 1 is equal to 2. In part A, we are asked to write the equation of the tangent line to y equals f of x at x equals 1. In order to evaluate the slope at x equals 1, we need to substitute the coordinates 1, 2 into the formula for dy dx. When we do that, we get dy dx at the point 1, 2 is 8. So the equation of the tangent line at x equals 1 is y minus 2 equals 8 times x minus 1. In part B, we are asked to approximate f of 1.1 using that tangent line equation. And we are also given that if f of x is greater than 0 for all x between 1 and 1.1, is that approximate value of f of 1.1 greater than or less than the actual value of f of 1.1? Well, first we have to find our approximation for f of 1.1. So let's use f of 1.1 in our tangent line from part A. F of 1.1 minus 2 equals 8 times 1.1 minus 1, which implies that f of 1.1 is 2 plus 8 times 0.1, which is 2.8. All right, so our approximate value of f of 1.1 is 2.8. Now the second part requires a little bit of thinking, some reasoning, and some understanding of number sense and some calculus concepts. Since d squared y dx squared is given by y cubed times 1 plus 3x squared y squared, and we're given that f of x is greater than 0 for all x between 1 and 1.1, we can conclude that y cubed is also greater than 0 for all x between 1 and 1.1. So if y cubed is greater than 0 for all x between 1 and 1.1, it is certainly the case that 1 plus 3x squared y squared will be positive on that interval as well. D squared y dx squared is the product of two positive factors for x between 1 and 1.1. Therefore, we can conclude that d squared y dx squared, the second derivative of f, is always positive on that interval, and that f of x will be concave up for all values of x between 1 and 1.1. If f of x is concave up for all values of x between 1 and 1.1, then our approximate value 2.8 will be less than the actual value of f of 1.1. In part C, we are asked to find the particular solution given that f of 1 is equal to 2. All right. Notice that dy dx equals x times y cubed is a separable differential equation. When you have a free response question and you have to solve a differential equation, if it's separable, you're almost always expected to use separation of variables. In fact, most of the time, if it is separable, there is a very punitive penalty for not using separation of variables. So if it is separable, make sure you use separation of variables. All right, so I take my differential equation, dy dx equals x times y cubed. That implies that dy over y cubed is equal to x dx, which implies that the integral of dy over y cubed equals the integral of x dx. Finding those integrals, we get negative 1 over 2y squared equals 1/2 x squared plus a constant. All right. Now we use the initial condition f of 1 equals 2 in order to evaluate the value of that constant. All right, so negative 1 over 2 times 2 squared equals 1/2 of 1 squared plus c. So we get negative 1/8 equals 1/2 plus c, which implies that c is equal to negative 5/8. All right, so now we have a complete function put together. Using the fact that c is equal to negative 5/8, we can rewrite our solution as negative 1 over 2y squared equals x squared over 2 minus 5/8. Solving this for y, we're going to get negative x squared plus 5/4 equals 1 over y squared. All right, solving that for y, we get y equals plus or minus 1 over the square root of 5/4 minus x squared. Right? And the reason we need the plus or minus at the moment is we introduced the square root. We don't know if we need plus or minus yet, or at least we haven't shown why we need one and not the other. But we can use the initial condition to reach that conclusion. Right? We're given that f of 1 is equal to 2. 2 is greater than 0. So for this particular solution, we better be getting values of y that are positive because we built this whole solution on a positive value of y. So we can conclude that y equals 1 over the square root of 5/4 minus x squared is in fact the solution that we want. Now notice that this function has a restricted domain. It is not defined for all values of x. Right? So we have to determine the restricted domain here. Right? Since we are taking a square root and we are dividing by that square root, the value of 5/4 minus x squared must be strictly greater than 0. Right? That implies that 5 minus 4x squared is strictly greater than 0, which implies that 5 is strictly greater than 4x squared. Solving this, we get that the absolute value of x must be less than the square root of 5 over 2, so my domain here is all x between negative square root 5 over 2 and positive square root 5 over 2. And that would be the domain of this particular solution.